Hello, everybody. We are going to wait until 100 people. This time it's going really fast. Well,
And we're
just a
there.
few seconds, we are there. So we just reached 100 live users or live viewers. Welcome to the OpenCV webinar, weekly webinar, and I'm very excited for today's episode because we have an exciting guest, Joseph Nelson, who is the founder of Roboflow and the CEO of Roboflow. And today we are going to work on a very practical episode, which tells us, why do computer vision projects fail? And in particular, why do deep learning based projects fail? What kind of data set selections we need to do? What kind of, pitfalls we need to avoid? So, and as always, we have Phil Nelson, who will be helping us out in conducting this webinar. And
Howdy,
without
folks.
further ado, we have already 220 people. That's great. So let's get started. I would start with an introduction. Joseph, you can take it from here. Please introduce yourself, and then we will dive into the subject matter. And just to give, before we start, I want to say that like always, we are going to do some goodies in the end. We'll ask a question and there will be a giveaway. And in addition, Roboflow would give away some discounts, etc. So please stick around till the very end. And this is going to be a very exciting episode. We will go over a chess game and we will show you, when you're trying to find pieces in a chess game, how can you, what are the things that you need to consider? What are the things that you need to be careful about while working with this data? So Joseph, take it from here.
Thanks so much, Satya. Joseph Nelson, co-founder, CEO at Roboflow. At Roboflow, we make developer tools so that individuals can create better computer vision models faster. Everything from collecting images, organizing images, annotating your data, pre-processing and augmenting, training up a model, deploying that model to production, and critically, closing the active learning loop so that your models continue to improve even once they're deployed into a production lifecycle. I'm really excited for today's conversation. I think that it is almost a little funny, and perhaps the reason that we've been able to attract so much interest that the OpenCV CEO and someone that runs a computer vision company are talking about why models fail. But we've seen it. It's all too common, unfortunately. So we thought it would be a good theme to draw upon for describing a bit more about how you can avoid those pitfalls. And just as Satya mentioned, we'll actually walk through a live example problem. If you've seen any of the Roboflow tutorials, we have our fingerprints all over creating chess object detection models. And in fact, that is the example we'll dive deeper with together as a group today. Now the chat is live, and it's awesome to see people being able to write and share. I always love to hear where folks are dialing in from, and be sure to continue to pipe your questions in as Phil, our excellent moderator, is doing things live. I do want to call one other thing out. So Phil's last name is Nelson. My last name is Nelson. We have no relation. However, I learned last night via Twitter that Phil is from Michigan. And so we're both Midwestern Nelsons. And so now instead of being friends, we are foes of who's going to be the best in the Midwest.
No thanks, Iowa.
That's great.
Awesome. So yeah, Satya, I'll hand it over to you for us to kind of kick things off. That's a quick background on what we're doing at Roboflow. I'll share my screen when we're ready.
Yeah, so I want to give you, a little story why such, this data, working with data is so tricky, because it's very easy to have these pitfalls. Even, people who are professionals, if they are not careful, it's very easy to make mistakes. My favorite story, it's from grad school. This is a story that my advisor tells me. When I was in grad school, Professor David Kriegman, he was my advisor. He told me about another grad student who was working in face recognition, and they were getting 100% correct results, right? It was perfect, the results. No matter how different, they changed the lighting on the subjects. They did a lot of difficult examples, but their algorithm was giving perfect result. And it so happened that the grad student, to save himself some work, he actually put a marker on every subject. So picture, let's say Satya Mallick is subject number 1 or subject number 2. So he would put a digit enabling, identifying that subject right in the picture. And he trained this model, the face recognition model. It was great because, it was actually learning the marker 1, 2, 3, 4 embedded in the picture, which was very easy to detect and identify instead of the actual person. So you can see that something which was very difficult now became very easy artificially because they had this additional marker that helped them. So that's that's a funny example. But I would actually let Joseph share your screen, and we can go over some of these typical pitfalls and how to avoid them.
How are we looking?
Looks great.
Looks great. Awesome. So, I mean, I give a bit of background on Roboflow and myself. I mean, in general, we help people accelerate their computer vision development through building tooling, and teams deploy better computer vision solutions faster. We're fortunate to work with many among the Fortune 500, some of the world's most innovative startups, as well as individual hobbyists and students alike. Roboflow really covers all parts of making the vision development process easier. And we're partners with OpenCV because we built with and our users build in tandem many of our solutions together. So I was actually just on a call earlier before this webinar of talking with a user who is using Roboflow for doing identification of specific cards. And then they use OpenCV to de-skew the detection of those individual cards. And this is a very common symbiotic relationship we hear between doing these sorts of processes. Now, vision is everywhere. And so here is just a sampling of random use cases. And the bolded ones here are just ones that we think are kind of fun. There's no real rhyme or reason to it. But 25,000 plus developers have built all sorts of different solutions, from identifying gas leaks to identifying if a ball was in or out in tennis line tracking, tracking and identifying endangered species. We had a Fulbright scholar build with Roboflow to be able to create basic better population and survey data on Safari. Airplane maintenance, lots of manufacturing and quality assurance problems where individuals will deploy their models to do otherwise manual processes through an automated way. Anytime there's an operator involved, making a visual check and identification is a place where vision can really help aid and add a level of rigor. One of the ones that people will often ask me, what's your favorite project that you've seen on Roboflow? And to be honest, that's sort of like asking a parent for their favorite kid. But I will say that some of the things that I've really been inspired by was we had a user that in the last year, as the coronavirus vaccine has been developed, there's been, of course, a really accelerated timeline to that development. One of the parts of that acceleration is doing faster quality assurance. So after the vaccine is developed, it comes out in these syringes, and there's a need to verify that everything from the stopper on the syringe to the top of the syringe to the level of liquid in the syringe is all correct before it goes to CVS, Walgreens, et cetera, for administration. And we had a user that a company that was working on a problem to do that automated verification faster. And that just sort of came in organically. And it was really impressive and kind of reminds me of, we're the vision experts, but enabling people to apply that to their domain has these incredible rippling positive effects across a lot of what we see. Now, a lot of these examples are places where we're talking about success, but we're here today to talk about places where that's not so successful. And I'll pull up the, overturn the rock, if you will, on some of those examples in a second. Satya, I'll give you a chance to introduce a bit about OpenCV for those that have little awareness, but I suspect that, everyone on this call might have a deep dive, but nonetheless, in your own words, it'd be great to hear.
Yeah, so this is mostly for Roboflow audience who may or may not have used OpenCV extensively. It is a 20-year-old library and started at Intel, and then it became open source. And for the last 20 years, people have been it's been run by volunteers, and we have over 2,500 different algorithms implemented in OpenCV. And deep learning is only one of them, but there are a whole bunch of algorithms, very optimized algorithms in OpenCV. In addition to that, people don't realize how popular it is. It is about, it's downloaded about 1 million times a week. So if you consider the C++ and the Python versions together, it's about 1 million times a week.
Wow.
So yeah, so that's quite a lot, and it's still growing. We are implementing new features, and the new version just came out, 4.5.2. So if you are not familiar with it, check it out. It is a very useful library to have if you're in computer vision.
I mentioned this, we're silver sponsors of the OpenCV library largely because of these reasons, right? I mean,
Yep.
Being a hallmark of 20 years of empowering developers to work with images, and now more and more with machine learning and deep learning based techniques, is something that we're, as open source contributors and developers ourselves, very eager to support.
Yeah, and OpenCV and Roboflow, right? The ethos are very aligned. Like OpenCV, Roboflow also believes in having this a lot of content for the users so that it's easy for the users. And there's also, we like building excitement together, and that's why you see that there are 400 viewers on this webinar today. That's great.
So let's dive into the success and failure cases. So Satya, your example of a facial recognition algorithm that in fact was a number identifier is a great example of a place to kick us off. Now, I mean, there's a lot of places where we're riddled with potential failures, right? And in general, every given problem, computer vision problem or any sort of technical challenge, any challenge generally, starts with a really good problem statement. Right, and this is kind of what defines the CV engineers that become and think about product, and the product managers that can translate down to computer vision problems, is this ability to identify and hone in on a good problem statement. And that's why that's kind of pulled out on the top part of the slide there. And then from there, there's kind of a common process that's followed on the technical implementation side of things. There's data collection, and we'll talk about tips and tricks to ensure that you use and identify good sets of data to build a good model. There's organization of those images so that maybe people across the organization can have access to it, knowing which images are going to be the best for labeling, because you want to be able to get to production quickly. Then there's the actual labeling of that data, annotating and adding and basically teaching the computer and saying, hey, this image in this bounding box is where we see a defect, or in this image, the tag for this overall image is raccoon versus fox. The unofficial Roboflow mascot is a raccoon. Then from there, there's pre-processing and augmentation. So this is where you take your images, and images come in non-regular formats. And there's decisions you need to make around, for example, resizing. A lot of the models that we build with assume having square images. Any model that has a fully connected layer in the neural network assumes having a square image to connect from one to the next, the way the convolutions are going to happen. So for example, resizing is a very common decision here, as well as augmentation. And taking, basically, you have a set of images and you want to make it be more representative of the conditions you work on. We'll talk more about what that looks like in practice with our chess example. There's training the model. And this is where, if you think about it, whenever you hear about computer vision or AI generally, this is where you hear the headlines. New model beats humans. This is where everyone's very, very excited and focusing on model this, model that. And the model is certainly important, but in the current view of artificial intelligence overall, the model, in my thinking right now, is overemphasized compared to a lot of these other steps. That's not to say it doesn't matter. It's to say that it is probably comparatively emphasized in comparison to, say, having a better representative data set. Now, nonetheless, we still need to train the model and have that model train and scale up to the size of our data set. We then deploy that model. And when we say deploy, we mean make it so our users can use that model in the context where they are using our system. So that might mean that there's a fully managed, say, cloud API where your system sends an image up and gets a response back. That might be on device. And when we say on device, we mean on the edge or with embedded technologies. So on the edge, you might be thinking about NVIDIA Jetsons, or some of these technologies that are small GPUs that you can use. Or you might be doing embedded work with, say, the OpenCV AI kit, the OAK, which is a device that has a 4K camera and GPU acceleration in a single device. The advantage here being that you could put that out in the field in a non-interconnected way, and be able to continue to run inference and whatnot. Then there's lastly, displaying the results. So this is where, your application is going to tell users what's happening and what detections are occurring. This is where actually the connection between your problem statement and the actual interpretation of your model is most key. So at the beginning of the call, I talked a bit about an example where there was a user who was doing card detection. And once they detected a card, they wanted to de-skew that detection. To be clear, the detection of the card would follow through the overall model process. And then the de-skewing would be a post-processing step applied, right? And that's how you would display it in the overall application. And then the final thing that you need to do is engage and use active learning, which is basically a fancy way of saying use your time efficiently. And when we say use your time efficiently, we mean if you're finding that your model is failing on specific examples, those are the examples where you want to improve your model's performance. So if this is a template for basically, like if you spend less time labeling examples that your model already knows and more time improving where your model knows less, then you get to production faster, you have a better improved model, and you can have a sustainable ongoing process. And this is why a lot of the time, this is an ongoing loop, not necessarily a one-time deploy, though that depends on of course, the context and problem you're solving. So this is the overall process of what success maybe should look like. But Satya, I'm going to pass it back to you for some examples of where things might break down in this process.
Yeah, so one thing that I would like to, like for active learning, when your scenario keeps changing, all right, then you have to be very, very proactive about active learning. I'll give you an example. So there was this company that created, a person detector where they were looking at people who were entering their store, etc. And it was working fine, and around winter, it started failing. And you would think about the normal things, right? Normal things like, oh, the weather is different and things like that. And all those did contribute. But the biggest contributor was that people started wearing these heavy jackets, right? And their detection model did not have enough examples of people wearing these heavy jackets and overcoats and hoodies and everything. So you see that you can easily, as the season progressed from say April to December, they started getting these failures. And if you did not have active learning in place, then you would keep failing. So, but there are other scenarios where things don't change at all. Like in a factory setting, you would find that the lighting is very consistent year after year, nothing really changes. And in that case, you may decide that, okay, we will train once in a while, it's not going to be active. But in many real life situations, it's absolutely essential to have active learning. The other thing I want to also emphasize is at the very beginning, when you collect your data, you should spend a lot of time with your data. Good data scientists are good data janitors who look at the data for a very long time. And you may think that, oh, this is beneath my pay grade or whatever. But just to give you an idea, in ImageNet Visual Recognition Challenge, there is human accuracy, right? There is this human who actually did did all the verification of a sample of the data set. And that human level accuracy is about 95%. You would be surprised that that human is actually Andres Karpathy, who is like one of the top guys in computer vision, right? He spent 7 days, or I cannot remember, I think more than 7 days on just looking at the data. And when he looked at this data, he got so much insight into what ImageNet is all about, what are the biases in ImageNet. For example, as far as I remember, there's a huge number of dogs in ImageNet. Something like 30-40% of the data is images of dogs. So there will be some bias when you try to do specialized tasks. So you have to be very, very careful about what data you collect, and also going through the data manually, right? Visualize your data and see if there are any biases, etc., so that you can catch these problems in the very beginning. And I know a lot of people who are so theoretical, they want to just not worry about looking at the data, etc. They just want to run a model, train something. and they run into, it comes and bites them because they have not spent the time with their data. It's almost, I like to say that, your data is like your spouse or girlfriend or boyfriend. You have to spend time with them to understand them. Otherwise, things are not going to turn out well.
That's a tweetable quote there. Satya says the data is his partner.
That's great advice.
We'll have the relationship coaching set next week with Phil. I think a common trend there is the emphasis on data and its importance to the problem statement generally. Can we double click on the idea of a good problem statement? And maybe you could walk through, Satya, some examples of where you've seen good and bad problem statements. And then after that, flip it back and I'll talk through in our chess example, what a good and a bad problem statement could look like.
So the problem statement is, when you define a problem, you should try to use as much information from the domain that you're trying to solve, and try to incorporate that. Don't try to solve a general problem when you have to solve a very specific problem. And you also have to define your problem very carefully. I'll give you an example. If you want to detect people, which is a very common problem, and you would think that, oh, it's a solved problem, just get a pre-trained model and it will work. And you would realize that it actually doesn't work. If you take a pre-trained model and try to use it in your specific example, it may not work. For example, you could have trained the data on a model that is trained for eye level, right? So all the pedestrians, the picture of the pedestrians are taken from an eye level camera. They look very different from pictures of pedestrians which are taken from a overhead camera looking down at the person. So you have to define your problem. This model is going to be used in this specific case. So just saying pedestrian detection doesn't, it's not enough. You have to say that it has to be pedestrian detection, and this is the particular use case. You could build something that is very general, right? But then you'll have to gather a lot of data. And in a lot of cases, that's not what you're trying to solve. You're trying to solve a very specific problem. So you could use that domain knowledge heavily. Similarly, think of whenever you define a problem, let's say in an industrial setting where you can control the lighting, etc. Don't try to make the problem unnecessarily hard for yourself. In an industrial setting, for example, you may be able to control the lighting, make it easy for yourself, so defining the problem and simplifying it is super, super critical. So I highly recommend that you spend the time even while defining the problem.
That's great. That's great. I think the calling on the one thing that's commonly missed in that is like a really good call out is if we're building a person detector, it's from what perspective? If we're building a chess piece detector, it's of what chess set, from where are we doing the chess set, right? And so if I want to dive into, problem selection, common issue number one of selecting a good problem statement, we need to select one that's specific, achievable, and drives results, right? And when we say specific, we mean both the perspective, what the outcome is meant to be, and ideally a level of accuracy as well. Achievable, we need to have a starting point. In fact, this sounds really intuitive. Who would pick an unachievable initial problem? And you'd be surprised. You would be surprised. The number of people that are like, oh, vision is the ability to see things in the real world. Let's say that you're using computer vision to help create valuations for used cars on a car lot, right? Now, you could say that in general, I want to have a model that's going to be able to price cars when you just snap a photo of the car. But in fact, that's actually quite unbounded problem. Perhaps you should start quite narrowly and say, I'm going to take a photo of the dashboard and identify the mileage, and that's going to be an input. Or maybe I'm going to take a photo of the each different part of walking around the car and look for scratches. Or I'm going to take a photo of the car and identify what specific car it is, right? And it's usually starting with that achievable baseline level, which then gets to the drives results question. Again, who selects a problem that doesn't drive results? But the answer is getting to an initial problem that both is minimally achievable, but still drives results is what defines a good problem statement, right? So going back to the used car example, a minimally helpful thing might be snap a photo of the dashboard and automatically create a model that identifies the number of miles driven, right? That doesn't solve the perfect valuation of the car, but it does probably solve the ability for, say, remote listings, or perhaps if you're purchasing like maybe rental cars for resale or things like this, that might drive a lot of business results. So you don't need an individual to abstract that specific piece of data. And so a good problem statement balances these considerations. I put an example of what I think to be a good problem statement in the context of a chess problem, and then an example of a bad problem statement. So I think a good problem statement would be something like create a computer vision model that can identify a chess piece and its position on the chessboard with 90% plus mean average precision. And it's okay if you're not super familiar with map and its measure. The point here is we have a specific way of knowing whether we're on a path to success. One thing that I didn't do here that maybe you should argue I should dive deeper on is from what perspective, right? Could the user be approaching with their mobile device on any which the angle, or is it always a common perspective? Is it any type of chessboard, or is it only the US Chess Federation board, as you see in my example image? And while I didn't call those out in my problem statement, as I likely should, we are going to make those assumptions in today's example, that it's a common perspective and it's a chessboard of the common US Chess Federation pieces. An example of a bad problem statement to contrast this, that's going to set yourself up for failure, is I'm going to create an app that helps users play chess with computer vision, right? And it's like, you probably could do that, but how and what? And like, how is it going to help them? Is it going to do move prediction? Like, it's the lack of specificity and identification of what's going to be successful in this example is comparatively unbounded. And like most things, having a good starting point and just being able to get started is far more valuable than waiting for a perfect solution where you can't start to derive some amount of business value.
Yeah, that's very well said. And you would be surprised how many people shoot for these unachievable solutions. They want, because computer vision actually competes with science fiction. People think that people are never impressed when you show them the latest and the greatest, because they thought that it was already done 20 years back, in the movie. So yeah, and I have, we are short of time. We are on the first one, but I have other examples. I have some great stories about how people picked unachievable solutions. I'll leave it for some.
Maybe we could save those for the end, or do a quick one now, and then after the hour we can have some after hours Satya tales.
So one example was that this company wanted to identify screws which go into the bones of people, and there are like 1,000 different kind of screws in X-ray images, and they only had, for training, they did not have these X-ray images. They had real images of these screws, which were RGB images, and they wanted us to build a classifier which would work on X-ray images. And I told them it's not possible, right? It's just impossible. They said that, no, our engineer has already built something which is 80% accurate. You just need to make it, slightly better accuracy. And I was completely blown away. I said, I want to learn from your engineer. And it turned out that they were working with 20 images, and the engineer under pressure had made it work on 16 of those images. And those, that would have never generalized. They were using some techniques from, the 1960s. And so, that's one example of something that was completely unachievable. But given those circumstances, the engineer was forced to work on it. So, it's not unusual. People try to come up with these examples which are very difficult to solve or impossible to solve.
I think sometimes people are trained to be able to summarize the problem in the simplest possible way, and so they think that's what they need to do, but it's not really the case with these kind of solutions.
Yes. All right.
So I was going to summarize our problem selection identification here. So I think to summarize, like the having a problem that is narrowly defined, achievable, yet allows us to drive some amount of business outcome, or at least solve the problem we're trying to tackle, is a good initial starting point. Now, I understand that that's sort of, the tough thing is it's hard to give general advice when it's a case-by-case basis, right? But in general, this is sort of the criteria you should run through whenever you're doing problem selection for a task that you're tackling. And this is also, of course, something where Satya and myself and those at the Roboflow team and OpenCV team are very eager to help with these sorts of questions, of identifying good problem statements and what's achievable and what's not. I think the second area that we've touched on that we should dive much deeper to is data collection and the quality of a given data set. And so I'm going to start with a little bit of the story in comparison. So you may be familiar with a data set in computer vision known as the COCO data set. Common Objects in Context is what it stands for. The COCO data set was released by Microsoft in 2014 as sort of like a benchmark for how different computer vision model architectures perform. Think about it like this. If you're trying to build a better model, you want to compare against a similar measuring stick, and the data set is the measuring stick. And so the COCO data set contains 80 classes across a wide array of common objects, if you will, chairs, fork, person, things like this. And it's used as a benchmark. Now, some researchers at MIT thought, what if we took a data set that had these common objects, but in a way that a human could clearly see what those objects are, but a computer might not, okay? And so they created the odd objects data set, which you can see on the right here. So if you're a human, as I am, hopefully you are too, you can identify these objects here. This one is a hammer. This is a chair. This is also a hammer. In fact, these very clear examples to humans, some of the world's state-of-the-art models decreased their performance by 40%. So you take a model that's trained on the COCO data set, and then you try it on what's called the odd objects data set, and the model fails. Lots of model failure abound. And I think that, in fact, the parable here of what this shows is not that we can't identify common objects. It's that the data that you collect and the data that your model is going to see in production need to be as similar as possible for you to expect to see success. And so to drive this home, I've underlined here, and if Satya's quote is around your data being your partner, my quote is your model is only good as the data is trained on. And making sure that you have a data set that is representative, of sufficient volume, balanced classes, and you're calling out explicit sampling bias, which we'll talk more about in a moment, to identify where there is and isn't sampling bias and correcting for it, is critical for success. So I can dive a bit more into each of these attributes of what success looks like for data set representation. Before doing that though, Satya, I'd love if you have another anecdote to share with us around data collection.
Well, I don't have any anecdote for this, but yes, there is one example. This came from Davis King, actually. I heard him speak once. Davis King is the author of DLib, and he showed an example of a fish data set. And again, this, the idea was that you had this plate of food, and some of those items were fish, like a salmon or something. And whenever the fish appeared in the data, it was a long fish. So the author, whoever published the data set, they actually turned the data around so that the fish was aligned. Some sort of people have this funny things. So it was axis aligned. It was always horizontal. But what that did was it created these black triangles on the sides of the data, right, of the image. Because when you rotate this, there are these missing pieces, missing spots where there is no data. You fill it with zeros, right? So you have these black triangles. And now fish, for fish, this gave perfect results. And basically what it was doing is that the network was identifying triangles, black triangles. Whenever it saw black triangles, it said that it is a fish. So that's that's a failure of data data collection. Another thought that I want to share, which you have already put in the slide about data collection, is the information that you want that your network will learn is in the variance of the data, right? To give you an example, it's not the size of the data set per se, but the variance in that data set. For example, you could have a 10,000 image data set, all of which are the same, right? You take a camera and record a video of 10,000 frames, and it has the same information, so it has zero variance. On the other hand, you can have a 10,000 image data set which captures the variance of the problem, So that's the most important thing. The variety or the variance in the data set is where the information lies, not the nominal size of the data. So you've already put it in more detailed way. But if you want to remember one thing, it's that you are capturing the variance of the data.
That's a really good way of putting it, because people are often asking a question of how many images do I need? And well, that's a good question. It's really a question of the variance of that sample, right? So maybe we can put this back in the context of our chess problem. Okay. So in our chess problem, you could have 1,000 images, but on the chessboard, there was never, we'll say, for whatever reason, the strategy you're playing got rid of the rook piece, right? And if you didn't have any rook pieces in your data set, you can collect all the images you want, but if there's just way too few of them, you can't expect to see good outcomes. And so it's volume is important. Variance is perhaps more important at a point. You can kind of think about it like you need to have more images, but those images need to come from the varied classes that you want to identify.
And also, it's only as important as the variance in your data. So you can imagine there is a classification problem. And let's say there are just two classes for simplicity. And one class is always yellow, right? And the other class is always blue. Then you don't need as much data, right? You have, 20 images and it will easily partition the data set into two. So it's when you are trying to get, the size of the data set would depend on how close two classes are in your training set. If you're trying to find different species of, say, dogs, that's a much harder problem than when you're trying to, separate the class dog from, say, buffaloes. So that's another point.
I think that's a really, really good call out as well. The difference between the areas you're trying to identify also frames how challenging the problem is, which is nice because that's kind of intuitive, right? Like me trying to identify different dog breeds, I only know so many, and I'd have to learn and get specific around learning the differences, similar to a model as well. Whereas if you just had like broad animals like dog versus shark, there's going to be wildly different contexts and hopefully much, much simpler in terms of the identification. I think this also calls out the importance of some of the ideas of what representative data collection means. And so in computer vision in particular, we're building systems that understand the world around us, which means that we need to take into consideration, especially when working with data that involves people, that we have representative data of our inference condition. And the nice thing here is the same sorts of ethical considerations of ensuring our models are reflecting a view of the world that we want is also one that drives model success. Put another way, if your data set isn't representative, not only is it perhaps injecting bias where you shouldn't be, but it's also going to be net less successful. So there's this really nice thing where having representative data sets that take into consideration the population your model is aiming to understand is also a business goal concurrently. And so there's really no reason to not consider the importance of ensuring we have representative data that is collected. And that's true even in when we're working with non-persons, having even just representative data of goods we're trying to identify defects of, or the different types of sushi. I saw a lot of folks in the chat really latched on to this sushi identification example, making sure we have this sushi that we're able to identify sufficiently represented. And so, you know, things like the device type, the location of the images, the lighting, the angle, and then lastly, making sure that you have a documented process of data collection and a means to continue to collect more data. To Satya's point earlier of the person detector that started breaking when people wore heavy winter coats, you want to make sure that you have a means to continue to collect additional data. And one other point here I'm going to zoom into is the idea of balanced classes. So here I'm actually going to shift over. Here, am I going to be able to shift over? Yeah. Here we go. So I'll shift over to, for example, and can I get a confirmation thumbs up from Satya that you see the chess stuff? Yeah.
Yes, sir.
That's great. So here, the chess piece data set, and I'll go to data set health check here. So when we talk about class balance, we mean making sure that you have classes that are generally pretty well represented in comparison of one to another. So specifically, it's not surprising that in a chess example, the pieces where there's only one occurrence of that piece, for example, the queen pieces, have a little bit less representation than pieces where there's lots of, right? Like the pawns. And in fact, if you train a model, as I have done on this data set, you'll see that reflected in the results. So in my chess piece data set, if I go to one of the models that I've trained, you'll see the results reflect that places where I have a higher representation of the classes of my precision by class is generally higher for those that I have represented in the data set. The other thing that's interesting is the model actually confused bishops and pawns, which kind of makes sense if you think about it, like the shape of them is quite similar. And that gets to Satya's point around that might mean we need especially more bishop pieces, because think about it, if the model is all things equal, it wants to guess between bishop and pawn, and it knows that pawns are a bit more frequent, then it might bias towards guessing pawn when it's, you know, actually a bishop. So increasing representation of classes, especially those where there could be a conflicting example between the two, is especially important.
And this is just to be, you did not mention it, Joseph, but this is the Roboflow interface, which allows you to do, this kind of analysis of the data, right?
Yeah, why don't I can just drop this link to this public data set is viewable by anyone.
Yeah.
And so you can actually take this data set, and if you want to play around with it, you can click fork, which will just create a public copy. Now, what was that on the OpenCV slide? What was it? How many forks you all have? 36,000 forks. So yeah, there's not 36,000 forks yet of this data set, but with your help, we can get there. So we'll talk more about this data set in a moment, especially around augmentation and whatnot. I initially just wanted to call out the class balance problem and the importance of thinking about where our pieces are on the board and how things kind of net out. Jump back in here. So data collection is a key thing that needs to be taken into consideration, and spending lots of time with your data set is critical. Now, a next common failure mode, and there's good questions that I see coming in the chat of drawbacks on augmentation or limitations or things like that, which we'll certainly address in our last 10 minutes or so. Now, one thing I do want to touch on, and we can go relatively quick because a lot of the themes are the same, but we get a lot of questions about this, and that's labeling and annotation. So, I mean, in the context of bounding box or object detection, we do bounding boxes. So here, we're training a raccoon detector. This data set is also publicly available. It's actually initially open sourced by someone named Dat Tran, who released this data set many, many years ago in object detection. And since then, we've seen more and more people like find raccoon examples. So if you see raccoons out in the wild or on Twitter, just tag @Roboflow AI, and we can get it added to the ever-growing raccoon data set. But let me talk through some of the labeling tips and tricks, if you think that'd be helpful, Satya. I don't know.
Yeah. That would be great. Yeah.
So when it comes to annotating images, basically what we're saying is we're teaching the model which pixels correspond to the object of interest, okay? So think about it. The labels that you make are tied to the business problem that you're solving. And so the rules, the quote unquote rules that I've displayed on this slide are not even, say, universally true. I know it's a little frustrating to put rules up and then say, don't always use these rules, but it's actually important to call out that decisions around, for example, if you label partial raccoons, or if you only label full raccoons, or if you label the tail of the raccoon or just the body of the raccoon, these are sorts of decisions, right, that frame back to the business problem you're solving. But nonetheless, I have a general heuristics for what most computer vision problems, especially those in object detection, come into play. So labeling around the entirety of the object is key, because if you only label part of it, then think about it, you're teaching your model. Think about your model like a finicky toddler. And if the finicky toddler only sees, one different part of the raccoon in different parts, it's not going to learn the overall picture of this is what defines a raccoon. You also want those labels to be pretty tight around the object for the same reason, because if you have loose boxes, then you're including irrelevant pixels. And our models are smart but brittle. They're smart but brittle. And so including a lot of irrelevant pixels will really throw them off. For occluded objects, occlusion means when one object is blocking view of another, we generally want to label the entirety of both of those occluded objects, even if they overlap. In other words, a frequently asked question I get is, can I label when two bounding boxes overlap? And the answer is yes, and you should. And the one that is being overlapped, in general, you should actually also label as if you can see the entirety of it. Here's an example in our chess data set in the upper left-hand corner. This white rook, right, is labeled even down to this edge here as if you can see the entirety of it, as well as the white bishop up here. And so we have these overlapping boxes, and we have pieces that overlap in view. That's generally the way that you want to label objects. For objects that are partially out of frame, you generally do want to label them. So for example, if I had an object that was partially cut off on my chessboard, I would want to include it. There are exceptions to that rule. In general, it's best practice to label even partial occurrences of the objects of interest. And the last thing here is sort of a joke: provide crystal clear instructions to the PDF. The bullet point should be clear in of itself, that providing crystal clear instructions so that others can mimic and follow your work is essential to create a reproducible process.
Yeah, it's about consistency, right? Because you are probably going to use many data labelers for a project, a big size project. And if their labeling is not consistent, it's a nightmare to deal with that situation.
I promise I won't label all the images with all of us on the line, but I'll just show an example here of a white knight. And actually, in fact, when I first labeled this data set, I would actually argue I didn't do a great job. I could have made these slightly tighter. I would argue I could have, but I mean, they're pretty good, but I'm maybe a bit hard and self-critical where things could be improved. And so this is an example of getting things labeled. One thing I do want to show, if I could, is data labeling takes a lot of time. And so one thing that we've been working on is making it so that you can automate your data labeling. So here I'm going to delete my hard work of deleting some of these pieces. That one's empty. Okay, so I have a few unlabeled images. Let me delete these ones as well. I'm not going to go through and delete all those. So okay, so I have a few images that have been deleted. I can actually load a model that I've already trained. So in this case, I've actually already trained a chess piece model, and then select which version. And I'm going to use this one here, which has a 98.7% map. And then what this does inside the Roboflow platform is loads that model so you can use it to label new images. Now, of course, the model is not going to be perfect, right? Like that's the entire point, is that the model has a first pass, but then there's places where we want to improve. But in general, it'll save us a lot of time. So if we turn this on and then we see that here, this actually automatically applied this annotation, and we can see it did get the black bishop. I might want to tune this up a tiny bit. Then I'll go to the next image here. And here, yeah, it got the white knight correctly. Let's go to the next image where there's a bunch of pieces. And there you can suddenly see, wow, this is saving us a lot of time of assuming that, each of these look good. And in fact, they do. And you can adjust this confidence as well. Say, we only want to automatically label things. If we have 90%, then we only get some of them, or label fewer of them, we get 10%. Okay, so that's just a small example of something that we've been working on to make this process overall easier. And that was the scope of kind of like our labeling and annotation common issues. I know that we're coming up towards the end of our time. So In fact, we actually outlined the first 3 common issues in this overall process. There are many, many, many more of places that we might want to dive into. But I think that, in fact, Satya, this might be a good time to welcome the Q&A of places where we can dive deeper.
Yeah, one last thing I want to cover is about augmentation and some of the pitfalls of augmentation before we start Q&A. Roboflow must have an augmentation. Do you have something that you can show right away?
I do. Yeah.
Okay.
So excuse me.
While you're bringing it up, I can tell one little story. This is a personal one. I made this mistake about augmentation. So when you're augmenting the data, obviously augmentation means that you take some data and then manipulate it or change it in such a way that you get, let's say, 10 times more data out of it. And Joseph will show that example, but you have to be very careful what kind of augmentations you choose. So one of the first projects I personally did, this was many years back, was about detecting Lego pieces. And there were these, I think 1,000 or 10,000 classes of Lego pieces. And I had turned on augmentation. I was trying to do all kinds of augmentation so that I get a lot more data than what was available. And by mistake, I turned on flipping, horizontal flipping of the data. And so basically you take the image of the original image and create the mirror image. And that also goes into the data set. Now you can imagine that it's a very bad idea for a Lego data set because in a lot of Lego pieces, let's say you have the wing of an airplane. That is one part. And a different part would be the right wing of the airplane. So the left wing and the right wing, they are mirror images of each other, but they are 2 different part numbers. So obviously my model got confused between the 2, and then I retrained it after removing this augmentation. So one has to be very, very careful about augmentation.
Yeah, for example, if we did a flip, and do you see this? You see this? Okay, I was trying to show the horizontal. Yeah. So if we did vertical flip, I don't think that would make a lot of sense for the context of our chess problem, unless someone's approaching the chessboard upside down. But in general, I think we'd apply a few augmentations here. Like I applied color changes. I applied a little bit of perspective changes. We could rotate things a little bit from either edge, and then we can maybe create 5 versions of this data set, and then generate this, and I'll just call it 5x aug JN. And what that does is it goes ahead and takes my training set, which is 202 images, and each of those are going to get turned into, each individual image is going to get turned into 5 output images. And again, this gets back to the point of augmentation is, the way I kind of like to think about it is if you're, say, doing a problem where you're trying to improve your model results, the source data is always the highest lever, that's the highest leverage point. But augmentation is another place where it's not a silver bullet, but it's almost like, in some senses, the closest thing to a free lunch in your process, where you can make things be a bit more representative. And just like we were talking about earlier, where there's a lot of variance or not a lot of variance, in manufacturing problems specifically, for example, augmentation is a godsend, because the types of defects we see, but in the lighting, we might have very few of those defects in our data set. And the conditions that we see might be similar as well, which means if we zoom in, zoom out, change brightness a little bit, change the color, orientation, it generally really helps improve the quality of our model. And we've seen that borne out at a lot of our examples with users on the Roboflow platform and elsewhere. And so now, you can see my data here has been ever so slightly augmented. You see the augmentations that were applied. And my data set is much larger now, so we expect that it will be a lot more performant, as just an example.
Great. Yeah, let's open up. I think we only covered, part of the thing, but we are running out of time. Maybe, we should do a follow-up some other time to, complete the training. There are pitfalls in training. There are the pitfalls. What we covered, I think these are the pitfall in data collection, annotation, etc. But then there is this other pitfalls also for training, deployment, display, everything. Yeah.
agree.
So maybe we'll do a follow-up some weeks later. Okay.
Cool. Let's do some questions.
Yes.
Great. Our first one here is asking about fine-tuning a model such as scaled YOLO v4. How do you get a lot of good quality data while avoiding overfitting that data? That's for either of you.
Yeah, I think
Joseph,
a lot of, go ahead.
No, you go ahead, sorry.
So to the question of getting good data for scaled YOLO v4, I mean, actually a lot of the considerations we talked about are model independent. So scaled YOLO v4 is, the latest evolution in the YOLO family of models. It took the YOLO v5 training architecture.
Oh, Joseph, you're still sharing your screen, by the way.
I'll turn that on. Cool.
Thanks.
So I mean, scaled YOLO v4 is the latest iteration of the YOLO family of models. It took YOLO v5's training framework and then applied it back to a lot of the YOLO v4 concepts from those original authors. To get better training data for scaled YOLO v4 is the same as getting better training data for any model. So a lot of the considerations we talked about are exceedingly relevant. I'd be asking questions like, are my classes representative of my inference conditions? Do I have the ability to put a minimum viable model into production that I can then start to use to see where the failures in my model are, and then only focus on labeling those examples to improve along the way. I think the concept of getting to a minimum viable production ready model, meaning it achieves a part of the business objective to provide an initial ROI, is essential. And then from there, the onus becomes on continued data collection and many of the considerations we talked about therein. So I don't think I have a ton to add from what we talked about around the data collection considerations, but Satya, if anything else specifically relevant to this comes to mind, I welcome it.
Not really. Nothing really comes to mind.
Okay. Well, let's move on to the next one then. We've got one here about, I think this is a really great question for both of you. What kind of questions should one ask to help differentiate between achievable and unachievable problems in computer vision?
So a rule of thumb is that if a human can solve a problem in 1 second, a human with minimum training can solve a classification problem in 1 second, then there's a good chance that you can train a model to do the same job automatically, right? Then you can, now if you consider that problem that I had said before, that if you show a human images of screws, it may be very difficult for them to see that in X-ray images. It's actually very difficult, right? So there is no chance a computer vision algorithm or any model would be able to solve those kinds of problems, right? So, and also, once you work on this thing for a long time, you get an intuitive feel, which is difficult to explain. How do I say that this problem would be solvable? But usually, if you're starting out, that rule of thumb is a good one. If a human can solve it with 1 second of inspection, maybe we can build a model with enough data to solve that problem as well.
Yeah, that makes a ton of sense. Thanks. We've got one here asking about, this is something I ran into when I first started learning computer vision stuff and annotation. What do you do with partially obscured objects in your data set? Would you draw a bounding box around them as though you can see them? Or should you, only show the part that is visible to you?
Generally label them in general. It depends a bit on the business problem of like, there might be a specific reason you only want to identify wholly visible things. And you might have a different risk tolerance as well for like the object you're identifying. But in general, you can err on the side of labeling and then including those as almost like a hard mode in your overall data set. So you should be thinking about like, one thing that like one sort of hack that I kind of do on this sometimes is you could label it, but even call it like hard class, right? So you label it, but you say like -hard. And then you can always drop that class. So you don't label the ones or you don't include the ones that are included in your training, or you can merge it with your main class. So let's say it's car, and the car is sometimes included, sometimes not. You'd have car -hard and just car. And car-hard and car could be combined to one class and train a model on it, or you could break them out and see them independently. So I would label it, if for nothing else, than optionality. And a lot of the times it's a good thing a good practice, so you can see how your model is doing with partial objects. One thing I will mention quickly is there's an augmentation called cutout that allows you to simulate occlusion. Cutout places black boxes on top of your images. It looks a little unintuitive as to why you might want to do that, but it's actually for this specific purpose of you want to simulate what it's like when an object is occluding another one. Satya, I'll let you say anything. Well, I'll share my screen real quick.
Well, there's one other thing I would like to add. This also becomes a problem selection. The thing about, we talked about problem selection. If it happens too often that your objects are occluded, right? It's a very common thing. Then you may want to think whether your problem is an object detection problem or an object segmentation problem, right? So in segmentation, you are trying to find which pixels belong to the object instead of putting bounding boxes around it, right? It's a different granularity of the problem. So, but if it doesn't happen often, right, then you put a bounding box around it, cover the whole object as if it was there. But suppose you are dealing with, some cells which completely overlap, like 50% of your data is overlapping, then you may want to consider whether it's, you may be wanting to solve a segmentation problem instead. Yeah.
Great. We've got one here asking about, say, for example, you don't have enough data for a deep learning model. Are there other classical computer vision methods that could be used in the absence of a really solid data set for deep learning?
Yeah, it completely depends on the problem. There are a lot of problems that can be solved using classical computer vision. Sometimes you can use the geometry of the problem. For example, you could have a depth perception, based on monocular, but suppose you have the option of putting 2 cameras, then you put 2 cameras and get depth using classical computer vision instead of trying to train a neural network to do a depth perception using monocular. So you have these other options, based on the problem domain. You should look at when enough data is not available, then you can use classical computer vision.
Yeah, thanks, folks. We didn't get to all the questions here. You had a ton of them. We'll try to. Yeah, we'll try to answer as many of these as we can, sort of offline. But go ahead, Satya.
So we have 2 prizes to announce, right? The first one is based on a question that we ask. Joseph, do you have a question we can ask our users? And the first one who answers the question will get a Roboflow T-shirt. It's a beautifully designed T-shirt. Or I can come up with one.
Let's do 2 questions.
All right.
I'll put you on the spot for a question, and I've got a spot. And by the way, these Roboflow T-shirts are not this Roboflow T-shirt. It's much cooler, in fact. It's a limited edition T-shirt that has a raccoon that we commissioned an artist named Von Dion to create. We then digitized his art and put it on shirts. We only give them out to contributors of the Roboflow blog. So if you're at a case,
did you create an NFT of it?
We did not create an NFT of it yet. I'm sure someone will do that on our behalf if we don't when we raise our $1 billion round. But the question for winning the first shirt, okay. And so let me be specific. You'll give your response in the chat. Okay, so and Phil will be monitoring the chat, and the first correct answer wins. Is that right, Phil?
You are absolutely right.
I'm going to give the question now. Hopefully you are ready. What is the name of the data set that a team at MIT compared to the COCO data set to demonstrate model error?
All right, we got odd objects. People started with COCO. Well, good try though.
What's the answer? Has it been answered yet?
Odd objects, yes. It's way up there.
All right, I'm tracking down who was first here. I took a screenshot. It looks like Andy G was the first one to post odd objects. Congratulations, Andy.
All right, so Phil, you would reach out to them and make sure.
I will do so.
So my question is, in the ImageNet net data, there was one animal whose images were in great proportion so that they could do fine-grained classification. Which species is it? Okay, great. That was an easy one.
What was the answer?
The answer is dog. And
Okay. Looks like Arun was the first one there.
okay.
We should do more trivia. This is great.
So so we are coming to the end of this episode. I want Joseph to, are there any other goodies that people can get, people who did not win from Roboflow? I always like to give, find extra stuff for our viewers to, get for free. So do you have something for the general viewers?
We do. We do. The randomly selected viewers will receive free Roboflow training credits and larger data set sizes. Kaylee on the Roboflow team will be responsible for reaching out to anyone that made it to the end of the presentation.
Okay. So, and they don't need to do anything for it. We have their email addresses from the Zoom call. Okay. That is it, folks. Thank you so much for joining. I hope this was informative, and we will do more of these so that people like yourself, some of you are beginners, even practitioners, get to know the tools and tricks of computer vision. That is it from our side.